Hello, this is my video on Project 1.3, the counting circuit. Within this video, I'll discuss each element, including the button input, the NAND gate oscillator, the decade counter, the decimal counting binary up-down counter, the binary counting decimal decoder, the 7-segment display, then the counting circuit PCB, then the counting circuit PCB case. The first step in the counting circuit is the button input. The LED's anode lead is connected to the positive rail, and its cathode lead is connected to the input. The input is high at rest, but when pressed, the output is grounded. This is called a pull-up resistor. So the next part in this project is the NAND gate oscillator. The primary goal of the NAND gate oscillator is to generate a square wave. So a square wave is a type of clock signal that oscillates between high and low values. This is the driver of the counting circuit. Next is the 4510 decade counter chip. The decade counter takes the clock signal from the NAND gate oscillator and then outputs it in 10 discrete steps. This bar graph displays each output of the 4510 going on in turn. However, in the counting circuit, the purpose of the decade counter is to divide the clock signal by 10. As you can see, the green LED is half the speed of the clock signal in the previous part. The next step in the counting circuit is to add the decimal counting binary up-down counter. This can either be a 4510 chip or a 4516. The difference between the two is that a 4510 chip, which is the one used in this counting circuit, counts from 0 to 9, while a 4516 chip counts from 0 to 15. The 4510 chip has a reset pin. When this pin is high, the count resets to 0. This pin is connected to a pull-down resistor. When this button is pressed, the pin goes high, and the count resets. Additionally, pin 10 on the 4510 dictates whether the count is up or down. This is controlled by a slide switch here. The count down is an active low count, and the count high is an active high. So when this is high, it's counting up as it is right now, but when it's low, then it starts to count backwards, as seen there. What this does is it allows you to link multiple 4510s to count a tens digit. Because the carry in pin of this, what it does is when it receives a high signal, it ignores all clock signals. However, when the count is low, when the input is low on the carry in, then it doesn't ignore the clock signals and the count advances. Therefore, every time the ones digit turns to 9, then the clock advances on the tens digit. So the next step in the counting circuit is the binary counting decimal decoder. Although the decoder is really just this chip, I'm showing it with the 7-segment display because there's really no way to display it without the display. So what the decoder does is it takes the binary inputs from the 4510 and it converts those into into 7 outputs that can be read by 7-segment displays to display them in decimal notation. And just like in the previous part, there's a pull-down resistor that resets the count to 0, as well as a slide switch that reverses the direction of the count. So as mentioned before, the 7-segment display is driven by the decoder, which takes the outputs from the 4510 and the binary outputs from the 4510 and then translates them into seven outputs that go into the 7-segment display that can be read by a 7-segment display. And each binary number corresponds with a certain number of pins that are high, which makes a decimal notation number. So this is the final product with a soldered PCB encased, screwed down with nylon screws. The final product still incorporates the up-down switch. However, there's only one 7-segment display and there's no reset pin. But yeah, thank you for listening.